Terrific. Okay, just count us in. Let us know.
We are live.
Hello, everyone. Thank you for joining us today. We are going to be announcing a new partnership between Wolfram Research and QuEra Computing. My understanding is this is going to be a big step improving the practical applications and accessibility of quantum computing. So, a lot to unpack there. By the way, we will be using some Mathematica notebooks in this little workshop, and all of the workshop notebooks that we use, we're going to upload them to the permanent versions of this video once we're done. So if there's any particular little line of code that moves too fast for you, it will be something that you'll be able to look through in more detail later. Although, of course, we'll try and be giving it to you at a pace that'll work for you now as well. I'm joined today by Mods, who is Manager of Academic Innovation Support at Wolfram. Also Nick, who is a Senior Research Programmer for Wolfram. And we have Alexei, who is a Senior Research Scientist at QuEra and a Visiting Scientist at Harvard University. And Yuval, who is the CMO at QuEra Computing. And without further ado, I'm going to hand this over to them and let them all explain what's going on and perhaps tell you a little more about themselves.
Excellent. Thank you, Noah. Hello, everyone. We are very excited, our first live stream, on our partnership with QuEra. What we are going to represent is the bleeding, edge of the technology, software and hardware. So, we are the software part, the QuEra team is the hardware part. And, together, I'm sure, we are going to have lots of fun. And I think, it's going to open new horizon to do quantum computation. So our plan, we are gonna start with some quick overview of the hardware. When we talk about QuEra hardware, what are we talking about? So Yuval will give a short presentation, and then together with QuEra team we have a conversation. We are gonna share a Wolfram notebook, and together we are gonna have a conversation how we can model and how we can basically simulate that great hardware and communicate with that from a Wolfram Mathematica notebook. Handing over to you, Yuval, please.
Thank you very much, Mads, and thank you, Noah, for having us in this live stream. I'll spend the next few minutes presenting QuEra and our computer, and then turn it over to the PhDs. In terms of who's speaking from QuEra today, my name is Yuval Boger. I'm Chief Marketing Officer of QuEra. I lead the company's sales and marketing efforts, and before QuEra, I was the CEO and Chief Marketing Officer of several frontier tech companies. And Alexei Belinsky, Senior Research Scientist at QuEra. Alexei is one of the first 3 hires at QuEra, helped build the technical team, led the development of our first quantum computer, Aquila. So he knows about Aquila essentially as much as anyone else. Alexei, thanks very much for being here today. About QuEra in general, we built and we operate the world's only publicly accessible quantum computer based on neutral atoms. We believe that neutral atoms are the best way to quantum, and we believe that QuEra is the most advanced of the neutral atom vendors. Our machine, called Aquila, has been live on Amazon Braket since November of 2022. We're working on and believe we have a clear path towards what we consider the holy grail of quantum computing, large-scale error-corrected device. So more on that in the future. One of the reasons we're able to do that is we have very close collaborations with Harvard and MIT, and we're able to productize innovations done by Harvard, MIT, and our people at record speed. Dozens of companies are using our machine either directly through QuEra or through Amazon Braket, and are publishing some amazing results, both in simulation, optimization, and machine learning. Companies based in Boston, we have more than 40 scientists and engineers from Harvard, MIT, and many other top-tier institutions. If you look at the history of QuEra, it's a history of breakthroughs. The company was started in 2019, spin out of Harvard and MIT. In 2021, we built our 256 qubit machine and launched it on Amazon in 2022. And part of that is driven by some of the innovations done at Harvard labs together with QuEra scientists. Most recently, we've demonstrated a new dynamic qubit shuttling architecture that allows us to move qubits while maintaining their coherence, and that opens the door for more efficient error correction code, for more efficient algorithms, and also recently demonstrated 2-qubit gate fidelity with 99.5 fidelity. So again, a crucial step towards error correction. The machine itself, 256 entangled neutral atom qubits, highly coherent, so you can do both some amazing things given the number of qubits and the level of coherence that we can achieve there. It is a dual mode architecture. We have analog computing today. I'll explain in a second what that is, and are working on universal gate-based models, so you can have the best of both worlds. And we have a technology called field programmable qubit arrays. It's sort of a takeoff on an FPGA. An FPGA is an electronic device that you could adjust its functionality in the field. And FPQA is an architecture that allows us to move the qubits, move the atoms, and use that to encode a lot of the constraints and a lot of the other things that we want to encode programmatically. So we have to take fewer programming steps because we let the physics do some of the work for us. Just running quickly, how do neutral atom computers work? Well, they're basically 3 building blocks. Atoms, we use rubidium-87, optical tweezers, and what's called a Rydberg blockade. So we have a rubidium-87 atom. That atom ends up being trapped in a laser beam, essentially sometimes called an optical tweezer. And that atom could basically, here's a photo of that atom, and that atom could today exist in 2 states. You can think about them as 0 and 1. We sometimes call them ground and Rydberg. And one of the interesting things is that when the atom is in the Rydberg state, it appears to be much, much larger, 1,000 times larger than it is in the ground state. And obviously we can drive it, we can take it from ground to Rydberg, from Rydberg to ground. And the interesting thing, the reason that size is important is what happens when you put 2 of these atoms next to each other. If the 2 atoms are sufficiently far apart, they can both coexist at the ground or the Rydberg state. But if they're closer than that, what happens is a phenomenon called the Rydberg blockade, which basically prevents them from simultaneously being in that high energy Rydberg state. And we can use that to encode optimization problems. We'll talk about that. We'll see a lot of these demonstrations in today's webinar. One last word on analog and digital. In an analog mode, you're basically defining the time-dependent Hamiltonian, the way the system evolves over time, and you can do that simultaneously on 256 qubits. Here's a photo of these 256 qubits organized in a 16 by 16 array. But we can also put them in other ways. Here's a map of the world, or we can also move them before and the computation and soon during the computation. And that gives us some amazing capabilities. And digital gate-based modes is what you know and love, gates that operate over 1 or 2 qubits. Digital mode is universal. You could do anything you want with it. Analog mode is more restricted, but then more powerful in certain applications. Specifically, we've seen amazing results both in machine learning, both in classifying and as well as regression and predicting of data. We've seen amazing results in optimization and also in simulation. So just to wrap up, before I hand it over back to Mads and the scientific team, there are 3 ways of working with QuEra. You could work with us, with our solutions team directly on building a proof of concept or figuring out an algorithm for you. You can access the machine either through Bracket or what we call premium access, which gives you business class service level agreements, and most importantly, direct support from our scientists to accelerate your quantum program. And then we also see instances where people want to buy or lease a computer, whether it's part of a national program or part of an HPC center integration, and we're happy to support that. So talk to me after the webinar, and happy to help you navigate this and find the best solution for you. And with that, Mads, let me turn it over back to you.
Excellent. Thank you, Yuval. So now let's see how we would understand, these neutral atom systems. So Nick, he's going to go ahead, share a screen, and, as a scientist, for us, the way that we understand, an atom is, or any quantum system, Alexei, if we know Hamiltonian, we know everything about that system, right? Like, and this is the Hamiltonian of these neutral atoms. So let's go through this Hamiltonian. Let's see how we can understand that. So Alexei, here we have three terms. What are those terms? And in simple terms, how we can understand them?
So this is an approximation still, doesn't include things like noise and other levels inside the atom, but this is a, assuming everything is coherent and the abstractions hold, this is basically an equation that will describe the evolution of your quantum system coherently. And the user in this case is going to be able to program some terms in this Hamiltonian. So let us go through term by term what these things mean, and how they are programmed. So maybe starting from maybe the most important one from the back, that pertains to this field programmable qubit arrays. This term basically tells you through this VJK coefficient which qubits interact with which other qubits and with what strength. Right, and this is a ZZ, what's called a ZZ interaction.
Yep.
And the strength of that interaction is proportional to a constant that has to do with the atom that we've chosen to use as our qubits, the C6 coefficient, and that is fixed for Aquila. But what is programmable by the user are these positions of the atoms. So they are these xj, xk vectors in 2D, so that they're actually pairs of coordinates. And basically the strength of the interaction term for any pair of atoms is inversely proportional to the 6th power of the distance between these atoms. And it's actually a fantastic way to program a quantum system because it's very visual. You can, the user positions these atoms in a plane, and you can visualize actually which atoms will be entangled with which atoms through the next neighbor interaction, basically.
So so then the first term is basically what we are discussing here is a two-dimensional lattice of atoms, and what we are saying is that each of them, they can have a very specific position. So the limitation is that the size is about 74 to 75 micrometer. I think that's the limiting size of this rectangle for 256 atoms, and the minimum distance between them is basically 4 micrometer. These are the only constraints. So within this rectangle, with the constraint of they cannot be closer than 4 micrometer, we can throw everything there, and we can have, for example, a simple lattice, a simple configuration like this.
Yeah, so first of all, it doesn't have to be a lattice, it doesn't have to be a regular pattern. Like you said, as long as the constraints are satisfied, it can be kind of an arbitrary arrangement of atoms, which is nice because it gives a lot of degrees of freedom in encoding your problem of interest into the atom positions. We'll probably cover how that is done specifically later. One additional constraint that I'd like to add to what you mentioned, so there's a minimum distance to which you can bring the atoms next to each other, and that has to do with kind of fundamental limits on optical diffraction. Because the way that we bring these atoms together is we trap them in the foci of optical tweezers, and then we need to bring those tweezers together, and the optical interference between these tweezers limits how close you can get them. Another limitation that is not fundamental, but is in practice there because of the way that we set Aquila up, is that for large arrays, if you want to get to large numbers of qubits, you have to kind of discretize this arbitrary pattern into rows. So if two atoms are close to the same y position but not quite, we basically kind of force them to be at the same y coordinate, because of the way these atoms are arranged by us according to the user request. So we basically arrange them row by row. So each row is arranged all the atoms in the particular row are arranged simultaneously, and then we go to the next row. And so that kind of puts an additional constraint on the space of possible geometries.
Okay. Now, given this geometry, so when we fix the geometry, which is basically the number of sides, we can have basically what Alexei just explained is basically this like this is a good visualization for that. So given this geometry, basically, like, let us assume the case that the geometry throughout the process is fixed. So it means, like, Nick, if you scroll up to that Hamiltonian term, it means, like, the interaction. So by setting our, like, site's location, we are fixing that interaction VJK. So those terms are fixed, which depends on basically the distance between, like, two atoms. Now, the other option that we have are three other parameters that are basically rabbit drive, detuning, and phase. So what are they? How, our user should understand those three parameters?
So first of all three of those pertain to the strength of the laser that is used. Sorry, they pertain to the basically the waveform that we apply on the laser that is used to drive those atoms between the ground state, where the atoms don't interact with each other at all, and the rhythmic state, where the atoms interact with each other according to these VJK coefficients. So in addition to arranging the atoms, the user can control the coherent evolution of the atoms between these non-interacting states and the interacting states. And it's basically a sinusoidal wave that you can control the amplitude, phase, and frequency of.
Okay.
And so,
now, like, in the most generic form, we have, like, the subscript J for the location of, like, rabbit drive, like, omega, and phase phi, and, detuning delta. In reality, do we have, as a user, do I have this option to have different rabbit drive per site, or all of my atoms, they are going to experience the same rabbit drive?
Yeah, so that's a good point. So in the Hamiltonian that's written down here, the omega, the phase, and the detuning have the subscript. However, currently in Aquila, it is a global parameter. All three of those, they're global parameters. So this drive that takes the atoms between the non-interacting and the interacting states is applied uniformly across all the atoms. One feature that we're working on towards putting into service is local control of the detunings. So that would be local control of frequencies through this delta J coefficient over there. Yeah, that one. And that was going to open up a number of applications because you can think of that whole term as basically a cost function in some kind of optimization problem. And now you can have many more degrees of freedom in defining that cost function by having local coefficients to it.
Okay. So let us start with a simple case, like, in Wolfram Mathematica, we have a function Aquila Hamiltonian, which takes basically four terms, like, at this level, like, remember, like, sites, omega, phi, and delta. These are, like, the terms that you have to specify. And this is the way that we understand, like, that Hamiltonian on the top. So the sites are basically, like, a list of positions X and Y. I don't know, like, Nick, let's go with the simplest case. Let's put one atom at the origin, 0, 0. And then, like, we can, for omega, we can go, I don't know, let's give a value. We would like to see some, oscillation. I don't know, the 1, 0, 0. So this is the case that we only have rabbit drive and nothing else. And this is the Hamiltonian for one single atom. This is the form, the usual form in bracket notation that we do. And the way that we understand it, like, in our framework is like this. So this Hamiltonian is basically responsible for the evolution of your atom. So we are going to evolve our system in a time, basically, frame using this Hamiltonian. The object that we have in our framework for evolution is quantum evolve. Okay, so you can evolve any quantum object. And here, let us, like, evolve our quantum system, which is describe our quantum state. So we would say it's Hamiltonian. And then, like, for us, we would like to specify time, for example, from 0 to 1. And you see, like, this is what we see. Like, now the result of this evolution is a state function whose amplitudes has time dependency. Okay, one thing that we can basically extract out of this state is basically the population, which is the probabilities, the modulus square of, like, each of those terms. And let's look at that. You would see, like, a function that looks strange because, again, like, those are the functions, they depend on time. And let us specify, I don't know, a specific time. For example, the second option, Nick is saying that, the time is 0.3 microsecond. By the way, I forgot to mention, like, everything is in micro scale. The sizes, like, is micrometer, and like, the time here is microsecond. And before one technical detail, Alexi, if I remember correctly, in the actual hardware, the time scale of, like, our evolution is about 4 microsecond, right?
That's right.
Okay, so remember, like, our users, like, you have absolute freedom, like, at this level to set your time whatever you like, but when it comes to the actual hardware, keep that in mind, like, 4 microsecond. And now let's look at the probabilities. At that point, Nick is showing you basically, like, the very first, we can call it, like, the Ridley population, and let's increase the time. Maybe 1 second was not the best. Let's change that. Let's go to 4.
So what are your units for frequency, I guess? Are they megahertz, or are they?
They are basically, like, we can understand it as megahertz, or you can understand it as, like, rod per microsecond. Yes, so, like, they are all megahertz. So basically the same convention that we have in the hardware. For example, maybe Rabbit Drive, you put it, Nick, as 1. Maybe if you put it as 10, we would see bare oscillations there. So let's put it at 10. And let's evolve our system for 4 microsecond. And let's look at, like, the probability. So you see that that's the usual, like, the famous Rabi oscillation is a textbook example that we have. Okay. Of course, like, this is the simplest case. And as, like, Alexi mentioned, you can play around your 4 time dependence parameters. So you can give, I don't know, like, time dependency to any of your parameters. For example, let's do as the next example. Without showing the simulation, let's understand, like, Alexi as a physicist. What's going to happen if we give time dependency to detuning? The same Rabbit Drive. Now, if we give, like, some time dependency to detuning, what's going to be the effect? Like, how would you understand that?
So it is important how fast or slowly the detuning is changing relative to this dynamics that you see over there, of course. But one typical protocol that is maybe very easy to understand is if you start with a strong Rabi drive, but a large thing, so that your Rabi oscillations are actually not these resonant ones that you show here, but actually they're really fast, really small amplitude oscillations. Effectively, they're, it's a population oscillating around the ground state, right? So you start with a large negative detuning, and your population is in the ground state with, like, these fast, rapid oscillations. And then if you ramp this detuning through resonance to a large positive value, the system actually wants to be in the Rydberg state. So atoms want to be in this interacting state, but with fast, rapid oscillations around the Rydberg state. Except that these interactions between them, set by those Vij coefficients, by the arrangement of the atoms that the user requested, they prevent atoms that are next to each other from both being in the Rydberg state. And this protocol of basically sweeping the detuning through resonance from a trivial ground state, where all the atoms just want to be in the ground state, to a non-trivial many-body ground state, where all the atoms want to be in the Rydberg state, but they block each other, neighbors block each other from being there. That is a way of preparing, what's called adiabatically, preparing a many-body ground state of the system, which has only one excitation per edge of the graph that you're encoding effectively.
Excellent. So just like, to understand, like, how we would model, like, what Alexi explained. So let's do this step by step. Right now, all the, the very first example that we showed you guys, you remember, like, this site was only 1 atom at the origin. Like you see inside the ocular Hamiltonian, it was only 1 atom. Okay. And those other terms, like, you can have any time dependency there. we want to move on to the case that, like, we have more than one atom. But before that, let us consider the second example, still one atom, but let us consider the case that the tuning has this, time dependency. So the amplitude is the same, as strong as, like, rabbit drive. You see, like, the basically compare the blue line with the orange line, but this time, like, the tuning, oscillates. And again, let's, like, drive our system, like, quantum evolve of, like, using this new Hamiltonian with this new drive, just to show, like, this simple, time dependency effect, 4 micrometer. And let's look at the probability of the, again, the very first one, which will be similar. Yes. So you see, like, this time, like, those, like, changes are basically due to the effect of, the tuning. And of course, here our detuning is, like, a sine oscillation. The adiabatic case that, Alexei explains, like, you go start from, for example, a negative value, and slowly you ramp it up to a positive one, which is the next case that we want to study. So, basically, like, this is the simple case, and I highly recommend, like, the users, like, it helps to play around these three parameters, like, rabbit drive, detuning, and phase, to understand how they basically influence the behavior of, like, each single atom. And of course, the headache starts when you add the second one and more, because that's the time that we have interaction between different atoms. Okay, so that's basically, yes, like, omega, what we usually call as rabbit drive, delta, detuning, and, phase. And by the way, like, one single note for the, like, or, maybe technical, but because we have the laser field here, Alexei, please correct me if I'm wrong, we are treating laser fields as classical system. We know that laser is truly quantum, but they are very strong. In this modeling, the Hamiltonian that we showed at the top, we are treating basically the light as a classical field, which is a very good approximation. So just right, Alexei, like,
That's correct. It's a time-dependent part in the Hamiltonian, where basically, it's a drive term that has a time-dependent amplitude, frequency, and phase.
Okay. So let's move on to the case of, like, interaction, between different atoms. And I don't know, like, how many shall we consider? 3 atoms, 2 atoms, like, the Rydberg blockade, like, are we okay with only 2 atoms? And, like, how would you like, Alexei? 2 atoms is good.
Well, do the 2 atom case, because you can prepare them both that way.
Okay, let's consider 2 atoms. So for our Hamiltonian, inside the site, so remember, like, now we case of 2 atoms, and, the term is basic. Now for the drive, like, how would you like to set it?
So the question is, there's many, there's a lot of flexibility in how you force the system to coherently evolve. So you could try to do what's called a pi pulse from the case where we have no excitation among the atoms, and a state where one of the 2 atoms is excited, right? You could basically do a square pulse for the amplitude at 0 detuning. Would be one way to prepare that state, the state of 0R plus R0, a superposition state of the left atom having the excitation and the right atom having the excitation. Or you could prepare the same state by using the adiabatic protocol we discussed before, where you start with a large negative detuning, maximum drive, and then you sweep through resonance to a large positive detuning. So both of those will actually give you the same final state.
So let's, like, one other function that we have, like, our framework is called, Aquila drive. And for simplicity, let's go with, like, adiabatic drive that you mentioned. For example, like, the very first term is the times, like, we can give it as a list. For example, we can start from 0, and then, I don't know, like, so time is the first one, then is, omega, basically rabbit drive, and then, yes, detuning, and then phase. So time, let's go 0, 1, 3, 4 are they good, and then let's say that like, we start, for the Rabi, 0, 15, 15, and 0. We basically go through this lamp. And the tuning, let us start with -30, like, the second one, -30, and then we jump to +30.
So it's not going to be a jump, it's going to be a sweep from the second to the third point, right?
Yep. Yes. And then, we can plot it. So the last one, the phase, let's set it as 0. Okay. So Nick, if you want, you can plot them for between like, the 0 and 4 microsecond. Let's everybody see like, how they look like. This is what we are discussing. So they look, oh, you drive. Yes. Yeah, that's what we are doing here.
That looks right.
Okay. This is what we like, that fancy term of like, adiabatic, evolution. It's basically setting something like this. And before doing the actual, basically, let's see, like, if we can understand the physics before doing any simulation. Alexei, what's going to happen to these two atoms? Both of them, we start from grounded state. Then what's going to be the contribution of like, so the last term is 0. So phase is 0. So what's going to be the contribution of rapid drive and also the tuning here?
Right. So basically, the drive is going to want to put the two atoms into the Rydberg state from the ground into the Rydberg state. However, when your detuning is large negative, which is where you start, it's a far detuned Rabi oscillation. So the population is basically stuck around the ground state for both atoms, right? And as you sweep through resonance, you actually go to positive detuning where, it's energetically favorable for the entire system, which includes, which for the entire driven system, which includes essentially the energy of the light and the atoms. It's more favorable for that system to have Rydberg excitations in the two atoms. However, there's an energy penalty for having both of them in the Rydberg state when they're close together. And that penalty is effectively that Vij term. And so, because you have placed your atoms at, I forgot what distance you used, but
now Nick, like, now that was the second question we wanted to ask you, Alexei. Nick is setting like, the distance as 4 micrometer. So what like that's the minimum distance. So what is the distance that like, you would like to set the second atom, Alexei?
Yeah, so at that distance, basically the atoms are close enough that the energy penalty is much larger than the energy gain in having both atoms in the Rydberg state. So basically, it does want to have at least one, but two atoms in the Rydberg state are too expensive in terms of energy at this distance. And so you will indeed see in the final state only one of the two atoms excited.
Okay.
But which one, there's no preference, and therefore you're actually going to end up being in a superposition state of those two possibilities.
Okay. So let's explore that. So basically, like, we set it, you see the first term in alkyl Hamiltonian is 2 positions that we set there. I think like, the T should be the symbol T, maybe, Nick, like, and then we see the drive is basically the one that you see in the line, 422. So that's how basically we evolve our system. Now, like, what we can do, we can look directly into the probabilities at a given time. So that's one way of like, looking at that. For example, like, at time 4, we can look at the probabilities. And here, if we look at the probability, we have basically 4 terms. So which of these terms are interesting? Like, when we talk about like, that superposition that you mentioned, Alexei, like, shall we look into each of these bit strings as we usually call them, or a summation of them, like, how we should go after our computation?
Right. Well, so these are actually amplitudes, right?
So these are the probability of each bit string. We can also show like, the amplitudes. For example, let's look at the amplitudes. So these are basically the amplitudes.
I think it's important to look at the the amplitudes first, because this tells you that there's actually, this is not a classical probability distribution. This is actually what you're creating is a superposition state, and you can look at the amplitudes. The first one is basically 0, and the last one is basically 0, but the second and the third give you this superposition effectively of 0, 1, and 1, 0. So that's a Bell state.
So it means like, you know, for that very specific case, you know, we can look at basically the summation of, you know, those two specific states. So what Nick is doing, like, you know, let's go, I guess, like, you know, that the state is 5 plus, Nick. So you should look at the, was it 5 plus? Yes, it's 5 plus. Plus, no, maybe, now I'm forgetting, maybe is it psi plus? Now I don't remember, like, you know.
Are these the names? Are these the names of different Bell states in Mathematica?
Yeah, so we have them. So the now plus, yes. Okay, 5 minus 5 plus. So we have them. By the way, like, you know, some of our users, they may say, oh, why you don't show us, like, you know, the usual bracket notation, like, you know, because I understand that bracket notation. The main reason that we show you that summary box, that originally, like, when you evaluate those codes, why you see that summary box, because that quantum object, it contains, like, you know, much more basically, like, you know, information compared to that bracket notation that you have. So that bracket notation is not the most generic way of, like, you know, representing, like, you know, that quantum object. That's why, like, you know, we show you, like, you know, the summary box. But of course, like, you know, if you feel more comfortable, it's simply, like, you know, a traditional representation. So what the short key that Nick is using is, you know, Command Shift T, which is basically literally traditional, like, you know, a representation of, like, you know, that state. And now Nick is bravely here. He wants to show, like, you know, the random pure state of, like, you know, 10 atoms. And, like, you know, you see here, like, you know, when you go to larger, now let's show the traditional form. I'm not sure if it's gonna, you know, render it, like, you know. So you see that bracket notation, like, you see, you don't get anything out of that. Okay, so that's one thing, like, you know, when it comes to a real computation, I know, well, like, when you are learning these things, those brackets notations, they might be useful, but when it comes, like, you know, to higher level, one has to be more careful. Now, why, like, you know, we wanted to show you, like, you know, that psi plus state. Now, Nick, if you scroll down, so Alexis said that, you know, the interesting term is get the amplitudes that correspond to that psi plus state and extract it out of your state and look at, like, you know, the probability, because that's where we have the superposition. So in terms of, like, you know, quantum, it means now I have to project my big quantum state into this subspace, which is basically psi plus. And now, like, you know, Nick, you know, what you can do is, like, you know, let's just, like, you know, do that projection. The traditional way is going to be the dagger of that quantum state acts on the original state at a given time. So remember, like, you know, if you don't specify time, like, you know, you would get a symbolic number, which is an interpolation, depends on time. So let's go with, you know, quantum state plus, instead of psi 1, put it as quantum state. Yeah, that one. So that's basically what we are doing there, okay, which is trivial. Now, Nick, do psi plus on psi 1. The last line that you had, yes. Okay, and now this is the term at a given time. This is the amplitude. Of course, you know, we can ask for, you know, modulus square of that one to get the probability. You know, what Nick is showing you is like basically, this is the textbook representation that you guys are more familiar with, right? Like, you know, you basically take the conjugate transpose of that one and then, like, you know, apply it to that state and you project it to that Bell state. Okay, so that's the amplitude at, like, you know, time at a specific time. And since we are interested in the probability, let's take the absolute square of that term, absolute square of line 441.
I'm just gonna take a norm.
Or norm, which is basically, like, you know, that's a different way of, you know, doing that. And let's look at the actual scalar. Let's just look at the number, which is the number that you see. As you know, Alexi mentioned, it's very close to 1, which is what we expected. Now let's plot it for the whole time from 0 to 4. Let's see what happens to that number. So now you should take the term, where was it? Like what line you have it, and then set 4. So it's gonna be like, set 4 as your time, and then
We want the actual dependency on time, right?
yes, we want to see that projection as a, yes, as a function of time from 0 to 4.
And do it like this.
Yes.
Good.
It should be much faster than this, but let's see, it's doing some grinding as we are waiting for that. So, and that's, the plot that we got. Now, how we should understand it, Alex, that's exactly what you explained, right? You remember, guys, he said, look at the second and the third amplitude, and they're almost one. It means we have the Bell state. Look at the evolution slowly, we reach the probability of 1 for that Bell state.
Right, and you can see this adiabatic transition basically from basically a state that's orthogonal to it to this Bell state as we go through resonance, and the resonance is basically in the middle of this time evolution too. That's where it's actually roughly 50-50 position, and you see the little wiggles that have to do with these off-resonant Rabi oscillations.
Yes. Yes.
So
now,
that's the adiabatic protocol in action. And one thing maybe to kind of lead a little bit into what you can do with Aquila in terms of variational algorithms is, we picked a protocol kind of intuitively. We picked the starting detuning and the final detuning and the rate of the sweep, and already we got pretty good final probability of being in the correct Bell state. But of course, you can now take those values and treat them as variational parameters and optimize this overlap with the Bell state that you're trying to prepare. And that is, the great flexibility in defining the waveforms is something that lends itself well to this kind of optimization.
Yes. So basically, what Alex is saying here is that, look, you could have any time dependency for your functionalities, which one is going to be useful for a specific goal. It depends on the problem. Now, let me again, for those of you who join us, what you see here is basically quantum framework. And, we had a few functionalities such as, Aquila Hamiltonian, Aquila Drive. These are, some new functionalities to help you to do coding easier for Aquila. At the very fundamental level, the way that we model this system in Wolfram Quantum Framework is we see them as a time evolution. You set your Hamiltonian, you specify the time dependency of your Rabi Drive detuning and phase, and you let your system evolve. How big you can do it for the system, it depends on the memory of your hardware. But basically, that's your main limitation. And this is it's basically any system that evolves those Hamiltonian, it is applicable. Now, what we can do with this? So what we can do is, one interesting application would be, I can set this Hamiltonian, I can get this result, and then through AWS, I can send it to our actual hardware. I can communicate with Aquila. So the only thing that I need to send through AWS is, what are the position of my sites? What are those 3 parameters, time-dependent parameters, basically the time series that we have for Rabi Drive, detuning, and phase. And I can get the result from a hardware. So here we are going to do some sort of cheating, because if you want to send the query directly to Aquila, it's going to take some time. I don't know, what's the wait, Alexi, what's the wait line, wait time right now? If we send a query, is it going to be fast? Is it going to be long?
Well, so today is Monday, so Aquila is not currently available on the AWS service. It's available every week for 48 hours from Tuesday through Thursday.
Okay.
But the queue currently is not is not that long. So
Okay.
I think if you submit it now, you'll probably get your results soon after the beginning of the window tomorrow.
Okay, good to know.
If you
Good
were
to
to
know.
submit it on Wednesday, actually, if we had this seminar on Wednesday, you would get your results more or less.
Okay, so let's do like this part, like it's a little bit cheating. So we already sent like one query to Aquila. We got the result from your hardware, so we can show you like Nick, show the like amplitude, phase, and the tuning that we sent and the result. So let's first we did like the case of like how many we had 9 sites, basically 9 atoms, and I guess somewhere there you also have like Nick, can you show like the rabbit drive that we sent there? So I think like it's in the notebook somewhere. Under AWS section, I remember like we also had a picture for the rabbit drive just for the sake of yes. So that's basically the job. Like if somebody wants to understand, look guys, this is the job that you're sending to the hardware. Like basically like it has 3 pieces. One piece is basically you are specifying the sites. This time like to go through like AWS, you have to convert them into micrometer. Okay. Which is easy, just add 10 to negative 6 in front of all your numbers. The amplitudes this time like you have to basically convert them into hertz, so that's why like you see those numbers. But anyhow, this is the job that we sent. And Nick, do you have any visualization for that? I guess somewhere in that notebook we also had a visualization just to see the actual, or maybe do we have it, or
like the actual comparison?
yes, like the rabbit, no, not the comparison, the rabbit drive, like what was the I guess like we went from let's see, yeah, that one. So this is basically the job that we sent, okay, which is basically again textbook example. And the data set that Nick is showing you, that's the result that we got from the actual hardware, and we need to understand like how we should interpret that. Let's look at like the measurement results. So Alexi, like in the measurement results, you guys return pre-sequence and post-sequence. As a user, how should I understand them?
So you had a very nice illustration earlier in your notebook where we had atoms that were initially loaded in the sites and then the sorting. Yeah. So
yes.
So when the atoms are loaded into this optical tweezers that are whose positions are defined by the user, actually only 50% of those sites are loaded. And what we do under the hood is move the atoms to the right locations so that the pattern is as the user requested it. Okay. However, that process can have finite error, and what we give our users is the result of that sorting step. So we basically tell the users which of the sites that they requested to be filled were indeed filled and which ones had a defect in it. So this is a good illustration of 3 sites in that array, a defect, and so that would be turned into a list of ones, except for zeros being at the indices corresponding to these empty sites, and that would be a pre result, so pre-sequence. Okay.
Okay. Got it.
Post sequence would be then the result of the actual computation.
Okay.
Where 0 would correspond to the atom being in the Rydberg state, and the 1 would correspond to the atom being in the ground. Or it might be the other way around. I don't know what the convention that you guys adopted in Mathematica, but
yeah. Now my question for you is this: does it mean like whenever I want to calculate like the probabilities and from the histogram and etc., should I select only the pre-sequence that all of them are 1? Or like that is that the meaning of like what you just explained to me? Like for example, if I want to,
it gives you the opportunity to do that post selection. Like for example, if you really care that the initialization is perfect before you consider the results, then yes, you can basically throw away all shots where the initial sorting or this pre-sequence has any zeros in it. or any zeros where you didn't want it to be a zero. Or depending, I mean, so it depends on what you're doing. In some cases, you might be tolerant to defects in your pattern, and in some cases, you might have even created, 10 parallel experiments in this region that's available to you. For example, with a pair of atoms where we were doing belt state preparation, right? You have more than enough space to create, 16 pairs of atoms in there, and you might want to keep the results for only those pairs that were correctly initialized and throw away the results for those that were not correctly initialized. So it's up to you how you process that data, but you have all the information available to make the decisions.
Got it. So basically, like, as a theorist, if I want to make a comparison, like, with my theory out of, like, by the way, like, in that job, you can specify the number of, like, basically shots that you can, like, send to Aquila drive, Aquila device. What we said was 1,000. And I think, like, the cost also depends on the number of shots, if I remember that correctly. But anyhow, as a theory, so my approach would be, I'm gonna basically, if I want to calculate the probabilities, I need to basically remove those 39 that the pre-sequence is not what I expected, but the rest, which is more than, like, 960, these are the one that they can tell me exactly, like, okay, like, I can do whatever I want, using, like, that data. Okay, so let's basically post-select those that, like, they look good, and let's look at, like, I don't know, the histogram of, like, 961, and let's look at the histogram. So what we are gonna see is, so that maybe not the best visualization. Yeah, let's do the counts and then bar chart. Yeah, that's better. So that's basically, and let's see. Chart label. Now I guess we have to rotate the chart label because they are very large, that,
Yeah.
Or maybe show the top 10, maybe from the counts. Let's just do the top 10.
I'm gonna cheat. Hold on.
Okay, yeah, you can rotate 90-degree the. Okay, you see, for example, like, the results that we got for that, 9 sites, as you can see, like, this is, for example, a very beautiful result that, like, for the probability of bit string. And of course, you can do all the comparison, like, with the theory, like, this exactly the same result that can become computed from the theory. So, and one thing I can tell from at least, a theory point of view, it's so beautiful because, look, I can do a theory. It's literally, as a theorist, I am doing an actual quantum experiment. It's like, it's a prediction, and then I'm gonna send it, and then I'm gonna get a result. So basically, we didn't show you this step of, sending to the actual hardware, but we practically perform a quantum experiment. Like, we did the theory part, and this is the result that we can get from our device. And then you can do whatever you want on the top of that in terms of noise analysis, compare, like, any, like, test you can do on the top of these statistics. There is a zoo of, like, possibility that one can explore here. And it's just the beginning. Remember, like, you have the option, go to a dimension of, 2 to 256. And, like, good luck if you want to do those simulations on your like, actual, like, the hardwares that we have here. I mean, classical computation, it's gonna be very challenging, if not impossible. So it opens up, like, a zoo of great possibilities to explore, like, quantum world. And one of them, I know, like, we have very limited time, but it would be a pity if we don't mention that. Look, these simulations, time evolutions, they have some very interesting application. And one of the examples that QuEra team, they have very nicely explored in their, white paper that was published, like, a couple of months ago, was the application of this system for a very important set of problems that are called maximum independent sets problem. Okay, so Nick, let's, it would be a pity if we don't mention that. Let's very briefly comment on that, and together with Alexei, at least, like, we can show the concept of, like, what we are talking about when we talk about maximum independent set problem. So I guess this time let's bring the whole computation that we had done. We don't have that much. So the concept here is this. Let's look at this graph. So we have a graph here, and the idea is that okay, pick vertexes, the maximum number of vertexes that you can pick out of this graph that there is no edge connection between them. Okay, mathematically, it's a very interesting problem, but you would be amazed how much application this simple problem has in the real world. Alexi, would you like to comment on some of the application of this simple problem?
Well, so this is actually an NP hard problem, and the associated decision problem is in the NP complete class, which means there's a vast number of problems that can be mapped onto it. Okay, but in particular for Aquila, there are some geometric constraints to the kinds of graphs that you could work with to find the maximum independent set, and because of this geometric constraints, it's actually all kinds of geometric problems fit very nicely. So things like finding the optimal set of street corners where you want to put your Starbucks in a way that you don't have more than one Starbucks at the neighboring corners, and this kinds of problems from the class of traveling salesman or optimization of combinatorial. These are all combinatorial optimization problems. We actually have a white paper that describes a number of such problems in kind of social networks and in finance, like hedge portfolio optimization, in logistics, and so on.
And by the way, the animation that you see here is that, in Mathematica, we have a classical algorithm to find, which is basically using the function that you see here, find independent vertex set. And you can look at all the solutions. For example, for this very specific graph that Nick is showing you here, we are looking for those, potential solutions to see okay, how we can find them. And the way that we model it, in this quantum system is, this is basically your site location. So literally the position of these vertexes, we are going to treat them as the position of your atoms as Alexi mentioned. So here it comes some limitation how you would basically model it, because you have some limitation in terms of the actual position. But then when it comes to the setting those three parameters, rabbit drive, detuning, and phase, what is the best setup, Alexi, here? Shall we go with adiabatic drive? And if so, why this is the right approach to solve this problem?
We have found that adiabatic works pretty well among the different algorithms that you can apply. Now, the parameters of this adiabatic drive can be further optimized through variational approaches, but even the kind of the naive one that we started with a simple sweep will actually get you a pretty good answer for a small problem like the one you're showing here.
Okay.
Why don't you go with that?
Okay, so then Nick, let's go with that. So let's see, let's set let's get the vertex positions. This is the rabbit drive that we are gonna use. Okay, so remember guys, Aquila drive is your favorite function whenever you want to set your three terms: time, rabbit drive, detuning, and phase. And we are setting the location here, we are saying that by the way, everything is in a in a sphere of in a circle of 1, and we are multiplying that by 5 because we would like to basically have Nick can show you the actual positions too, that where we set them. Yes, this is the actual position of those vertexes. Maybe list plot is a better, and yeah. And then, yeah, that's the graph representation. So that's how we set our Hamiltonian. Okay, so this is the Hamiltonian. We set the Hamiltonian. Let's evolve our system using this Hamiltonian. The rabbit, the everything the adiabatic drive, Nick showed you on the top. We have the sides. So let's just evolve this system.
Actually takes more time to construct the Hamiltonian than evolve it for some specific reasons.
Okay, and then what we can do, so this is our Hamiltonian. And by the way, like, you know, one comment, since, you know, Nick mentioned here, like, you know, the performance. We are doing everything in the most naive way, like, you know, we are doing summation, etc. There are much better way of, like, you know, doing these things in Mathematica, but this is the simplest way. So we have the wave function, and let's look at the probabilities, like, you know, basically let's look at the Rydberg population per site. So which means, like, you know, let's consider all the cases that specific site has, like, you know, the one. So that's how we can go after, you know, Rydberg population. And let's just, you know, plot them in time. And, like, you know, that's what you get. Now, as you can see here, for example, like, you know, a couple of them, like, you know, with the maximum probabilities. So these are the one that has highest probability of, you know, observations. I don't know, maybe Nick, do you want to plot the bar chart at the very end? Let's look at the very last one. Let's see, like, you know, how does it look like for the very end?
Hold on. What is?
Time final is 2.2, if I remember that correctly. Yes, 2.2 microsecond. And, like, you know, if we do that, I think, like, you know, the 6, 5, like, you know, they have the highest probability of, like, you know, getting the result. By the way, let me just be, like, you know, honest comment here. It doesn't mean you would be able to get the collection of all maximum sets. Okay, like, you know, if you play around, like, you know, with your parameters, like, you know, if you change, like, you know, the rabbit drive and etc., like, you know, you might get, like, you know, different results. But, like, you know, here you see, like, you know, for example, like, you know, 1, 4, look at, like, you know, the answers, they are the one with the largest probabilities, but, like, you know, from the quantum approach, we would be never able to get the result 3. Okay, so it would be, like, you know, a pity, but again, like, you know, we managed to get a collection of them. And by the way, this is the simplest approach. Like, you know, you can play with the rabbit drive, you have the freedom of, like, you know, changing them, and then, like, you know, whatever works better, you can send it basically to your actual hardware. One more time, Nick, if you scroll up, because there are a couple of questions, like, you know, they, you know, our users need better clarification. Look, the graph that you see here, each of the basically the vertexes that you see, this is gonna be the position of your atom. So literally what we are doing is, like, you know, it's like reflecting this exactly into a configuration that we have in QuEra. And then here, if all of them, like, you know, just the scaling, we did a scaling, and, like, you know, that is scaling, like, you know, which was very similar to what we did with, you know, you guys did it in your white paper. You know, we go with the factor of, you know, 5 micrometer, multiplying all of them, and that's how we set the position, and then the rabbit drive. So that's one of the many. And then again, like, you know, to all of our users, both hardware and software, it's just the beginning of, like, you know, this whole story of, like, you know, doing quantum computation with these hardwares. It's like uncharted territories. It's just open, as I said, a new horizon, and users, by all means, just dive in and explore. I'm sure, like, you know, you will be able to find, like, you know, lots of new things that we had no clue that you can do, lots of interesting computation using, like, you know, these systems. We are almost out of time. So Alexei, like, you know, you all, any final comments, any comment about the simulation that we just showed to our users?
Thank you, Mads. I think, as you mentioned, we just scratched, I'm sorry, the surface of what's going on here. There is the white paper that you mentioned, and a beautiful Mathematica notebook that goes with it, that goes through 5 examples, I believe, from simple to very sophisticated.
Yep.
The QuEra team is happy to answer any questions about how to use this for machine learning, for optimization, for simulation. There's also a Slack channel that you're welcome to join for QuEra questions. And we look forward to seeing you in the Hilbert space.
Alexei, like, you know, any final comment, like, you know, anything you would like to add here?
A good way to visualize results is actually plot the probability of distribution of bit strings rather than per site.
Very good point.
And you have one above for the regular array. If you scroll up to it,
Nick, show that, yes, go up,
go high before the MIS.
Before this, example.
When we were doing the regular array, yeah,
This
you
one,
see that?
yes.
So you see that the highest probability bit string over here is actually this ordered phase 0, 1, 0, 1, 0, 1, 0, 0, 1. That is actually the maximum independent set on the square array of atoms that you programmed for this example. That is indeed so you found with high probability the maximum independent set. And for those who are physicists out there, that phase is the antiferromagnetic ground state of the system.
Very good point.
So this kind of illustrates both use cases that you can work on Aquila. That's kind of like combinatorial optimizations and the kind of ground states of many body systems. They are kind of two sides of the same kind of hardware capabilities that we offer.
Yep. So like, Nick, if you want to do the probability, I think the probability is almost close to 1. Like, yes, but just looking at those
just
numbers.
compare the counts.
Yeah.
But
let's normalize that by total and like wrap it by a number. And so you see, like, that's the probability of like, getting the right answer. So basically, even the previous example that we were showing you, because it was a simple lattice example, it was actually finding like, the maximum independence set.
That's right.
So as you all said, like, both teams, like, we are looking forward to see, more application on these devices. Like, they are, we are just at the beginning of like, a big revolution, and we would love to see the contribution of like, both community of users, Aquila and, Wolfram Mathematica. Please reach out to us, like, you know how to find us, quantum@wolfram.com, and both teams, we are looking forward to have more interaction with our users. Thank you, Alexei. Thank you, Nick. Like, Noah, everyone, like, you all, it was great. I'm very happy about this partnership. And as I said, you will hear from us much more.
Thank you so much, Matt. Thank you, Nick.
Thank you, guys.
thanks, guys.